Welcome to the 14th lecture of the course Discrete-time Markov chains and Poisson processes. So, recall that in the last lecture we have talked about what is called recurrent state and what is called transient state, and to define those recurrent state or transient state we need what is called first passage time. So, we define first passage time, which basically mean that after the time 0 is excluded when the chain will visit for the first time the state I, okay? And then if the probability of visiting the state I in finite time for the first time, given that the chain is starting at the state I is 1, we call such states as a recurrent state. If it is strictly less than 1, we call such states as a transient state. Okay? And then we talk about the fact that, well, in case of the recurrent state, that basically mean that starting from I, if I is recurrent, then starting from I will come back to the state I again and again. Okay? And it was basically a if and only if condition that I is recurrent if and only if that probability starting from I x n equals to I for infinitely many n is 1. Okay? So, I will visit the state I again and again starting from I if I is recurrent. On the other hand, if it happens that starting from I am keep on visiting the state I after some time, then I has to be recurrent. Okay? So, those things we have seen. Then we talked about what is called kth passage time, which is nothing but after time 0 when the time at which the chain is visited the state I for the kth time. Okay? And then we have defined what is called the length of the excursion, which is nothing but the time difference between two consecutive visits to the state I, and we see what is the distribution of Si. Okay? What is the distribution of Sik that we have seen. So, with that we start with today's lecture, and today's lecture we are going to talk about what is called number of visits. So, number of visits is just what is basically mean that how many times the chain is visited to some state. Okay? So, definition goes like that: for a state I, we define the number of visits to state I by this particular quantity. Just recall that we define delta I x to be 1 if x equals to I and it is 0 otherwise. So, that means basically that if x n, so that is basically nothing but the number of time x n is equals to I. Okay? Number of time x n equals to I occur. So, I am taking the collection of all possible values of n greater than equals to 0 such that x n equals to I, and I am taking the cardinality of that set, that is basically this one. So, that basically mean number of times the chain entered into the state I. Okay? Number of time the chain enters into the state I, that is basically nothing but our Vi, and Vi is called number of visits to the state I. Okay? So, now what we are going to see is that what is the distribution of Vi. To show, so the distribution of Vi is given here, which is basically that for k anything between 0, 1, 2, so on and so forth, the probability that Vi is greater than k is given by Fi to the power k, and this is a conditional probability. So, this probability, as we know, it is nothing but probability that Vi greater than k, that starting from x naught equals to I, that is basically Fi to the power k. And what is Fi? Fi is nothing but probability that starting from I, what is the probability of xi is less than infinity. Okay? So, recall that when we define that recurrence and transience, we define in terms of Fi. If Fi equals to 1, we call I to be recurrent. If Fi is strictly less than 1, we call I to be transient. Okay? So, this is basically the distribution of Vi, and notice that if I know this quantity for all values of k, I know all kind of probability for Vi. For example, I can easily calculate this probability also. This probability is nothing but probability I, Vi is greater than Vi is greater than. So basically, if this point is k, then basically what I have to do is that I have to take the probability in this side, I have to take probability in this side minus probability at k plus 1. So, that means this is greater than k minus 1 minus probability I, Vi greater than k. And now, the first quantity from here is basically nothing but Fi to the power k minus 1 minus Fi to the power k. So, in this way I can able to find all the probabilities, all the probabilities for Vi equals to k, and if I get that, I can able to find what is, suppose I want to find what is the probability that Vi equals to 0 plus probability I, Vi equals to maybe 100. Okay. This now I can easily find out the first quantity is basically nothing but Fi to the power that Vi equals to 0, that basically 0, because that is basically well, k equals to k start from 1 here, because k, if I take k equals to 0, there is a problem. Okay, if I take k equals to 0, there is a problem. So, I can write this probability as probability of Vi is I make it 1, because that 0 is basically does not make much sense here. So, I make it 1, and then basically it is basically nothing but Vi is greater than 0 minus probability that Vi is greater than 1. This is basically the first part, plus I have the second part, that probability I, Vi is greater than 99 minus probability I, Vi is greater than 100. Okay. So, this way actually I can find all the probabilities. Just one thing, I by mistake I have written 0 here, but 0 will not be there, because that Vi equals to 0 does not make any sense in this case, because the thing is that actually that probability you can take as 0, because I am starting from I, and so I am starting from I, and n is 0 is included here. So, Vi has to be greater than 0 with probability 1, So, Vi equals to 0. So, I equals to 0 has to be 0, there is no other option for me. Okay? That is there, there is no other option for me. So, this way, that my main takeaway, my main point here is that if I know this probability, I can actually calculate all kind of probabilities, all kind of conditional probabilities regarding Vi when x naught is I. Okay, when x naught is I, regarding Vi, I can calculate all the conditional probabilities if I know this particular thing. Okay, so now we will go for proof, but to prove this one, we are going to use what is called mathematical induction. So, I know many of you know what is mathematical induction, but just recall that, or if it is new to anybody, that's for them to introduce to what is mathematical induction. Let us first discuss what is mathematical induction is, and then we will proceed to what is the proof of this particular theorem. So, the mathematical induction can be stated as follows. Suppose I want to prove the statement Pn holds for all n equals to maybe 0, 1, 2, so on so forth, or sometimes 0 may not be there, or 1, 2 may not, 0, 1 may not be there. Those kind of scenario occurs, but I am taking the most general case. So, for example, I may think of that Pn, the statement Pn is that 0 plus 1 plus 2 plus so on so forth n equals to n into n plus 1 divided by 2. So, in a problem of in the problem is that I am trying to prove that Pn is a statement which hold for all possible values of n. So, like Pn could be that statement. So, I may try to solve that the sum of first n natural numbers is n into n plus 1 divided by 2. Okay? So, the way of mathematical induction goes like that. We generally show the step 1, which is called the basis. Basis is that to show that P naught is true. Okay. So, to show that P naught is true, that basically mean in our example P naught is basically nothing but 0 equals to 0 into 0 plus 1 divided by 2. So, I take n equals to 0 here, and I show I need to show this, and this is trivially true. This is trivially true in this case. Okay, this is trivially true in this case. So, the first basis part is that I have to show that for n equals to 0, the statement is true. So, the first point, the statement is true, whatever the first point. If 0 is not here, if n start from here, then I have to show that this statement is true for n equals to 1. Okay. So, basis is that at the first point, that the initial point, the statement is true, that is the basic. Then we go for the induction step, and which is basically to show, we assume in the induction step, the assumption is that P k is true. That basically means that n equals to k. We assume that for n equals to k, the statement is true. We need to show that P k plus 1 is also true. So, we assume that for n equals to k, the statement is true. We want to show that for n equals to k plus 1, the statement is also true. So, for our case, our example, that basically mean that Pn, which is basically Pk, which is basically nothing but 0 plus 1 plus so on so forth, plus k equals to k into k plus 1 divided by 2. We need to show, we assume that this is the assumption, Now, we want to show, based on this assumption, we want to show that Pk plus 1, which basically mean that 0 plus 1 plus so on so forth, plus k plus 1, that is equals to k plus 1 into k plus 2 divided by 2. And how we can show? First part is that, note that this part is basically from our assumption in that induction step. This part says that it has to be k into k plus 1 divided by 2, and then I have k plus 1 here. I add these two, and finally, if you add this one to the algebra, you can easily show that this turns out to be this one. Okay, this turns out to be this one, and that completes the proof. So, the idea here is that first we will show that P naught is true, then we assume that Pk is true, and based on the assumption we will show that Pk plus 1 is true, and then I am done, because now because 0 is true, that so I can take k equals to 0, and it says that Pk plus 1 is true. So, P1 is true. Now, if P1 is true, then I can using the induction step, I can tell P2 is also true. Then because P2 is true, I can also now show that P3 is also true, and so on and so forth. Okay. So, that is basically the idea of induction, and to prove this lemma, we will basically going to use the induction. So, in our case, basically induction means that we will show that for k equals to 0, this statement is true. Then we assume that this statement is true for k, and we will show that for k plus 1 also this statement is true. Okay. So, in very layman's word, that mathematical induction can be put in this way. Suppose I am trying to climb a ladder. Okay, I am trying to try to climb a ladder, and the way we climb is basically step by step we go up. So mathematical induction basically tells that if I am in the bottom rung, if I am in the bottom rung, then basically the basis part is that I am in the bottom rung, that is true. I can stand on the bottom rung, that is true. And then induction says that if I am in the kth rung, then I can move to the k plus 1th rung. Okay? If I am in the kth rung, then I can move to k plus 1th rung. If this too is true, that I can be on the bottom rung, and then if I am in any rung, then I can move to the next rung. Then this says that, then using the mathematical induction, this says that I can climb as high as I want. I can climb as high as I want. Okay, that is basically the mathematical induction in very layman's word. Okay, so with this understanding, let us now proceed to the proof of this lemma. So the proof of this lemma goes like that. As I already pointed out, we will basically use the mathematical induction to prove this lemma. Now the first observation in this lemma is this one, that see that Vi greater than k. What is Vi? Vi is number of time the chain visits the state I. Number of time the chain visits the state I. So this part is saying the chain, the Markov chain visits the state I at least k plus 1 times. Okay, at least k plus 1 times, and so that obviously true now is that kth passage time has to be finite. Okay, if the Markov chain visits the state I for at least k times, then kth entering time, kth passage time has to be finite. So that basically, if I, for example, if I take k equals to 1, and what I am saying here is that the Markov chain has visited the state I at least twice, that basically mean that this is t I 0, then somewhere I have t I 1, and somewhere I have t I 2. Okay, and it has visited at least twice. So that means basically it may be this or it may be this. Okay, or if I start from something else, then this two has been visited. So finally is that if I take k equals to 1, then this time has to be finite. There is no question about that. This has visited at least twice, this has visited at least twice, so this time has to be finite. There is no problem. I mean, this has to be true. Okay, this has to be true. And on the other hand, if this is true, that this one is finite, then the Markov chain has to visit the state I at least once. The Markov chain has to visit the state I at least twice. That means basically Vi has to be greater than 1. That is there. Okay. So of course here one assumption is there, because always I am talking that I am starting from I. So this observation is true under the condition that x naught equals to I. Okay, under the condition that x naught equals to I, these two things are same. These two things are same. So this is I. Of course, this is I. This is I. So Vi is greater than k. That means if I take k equals to 2, then Vi is at least 2. So it has visited here. It has visited here. So t I1 has to be finite, which is basically this part. On the other hand, Vi1 is finite, that means Markov chain is I here, and then again it has visited the state I here. So Vi has to be greater than 1. Okay. So under the condition that x naught equals to I, that Vi greater than k and Tik is less than infinity, these two are same events. So if I try to find out the probability of I here and probability of I here, they has to be same, because the two events are equal, two events are equal, so their probabilities will be equal, but under this condition, because these two events are equal under this condition only. Okay. Now let us go for now induction. So first point is the basis point, this is the basis that statement is true for k equals to 0. Why statement is true for k equals to 0? The reason is as follows, that for k equals to 0, what happens here is that pi vi greater than 0. Okay. Now as I mentioned that what is vi, just let us write the definition of vi here, which is delta I x n, and n runs from 0 to infinity. So because n0 is included here, and this basically mean that vi greater than 0 given x naught equals to I. So vi is at least 1, vi is at least 1. So vi is always greater than 0. So clearly this is equals to 1. Okay. On the other hand, if you take fi to the power 0, because fi is a probability, is always lies between 0 and 1. So this quantity is also 1. Okay. This quantity is also 1, and now I am done, and the basis step is true, that for k equals to 0, this statement is correct. Okay. Now we have to assume that for this statement is true for k. So that means that we assume now is that it is true that the induction hypothesis is that for k equals to k, it is true. That means probability I vi greater than k equals to fi k. We want to show that vi greater than k plus 1 is same as fi k plus 1. If based on this assumption, if we can show this one, then we are done. Using the mathematical induction, I can now claim that this particular statement is true for all values of k from 0, 1, 2, 3, 4, so on, so forth. Okay. So let us try to prove that. So we assume that at k equals to k, this is true. I want to show that for k plus 1, this statement is true, which is basically given here. So let us go through it, how we can prove that. Okay. So vi starting from I, vi is greater than k plus 1 is same as starting from I, ti k plus 1 less than infinity. These two events are same, so their probability has to be same. These two events are same because of this, but this is basically conditioning on x not equals to I. Okay, conditioning on x not equals to I, and that condition is kept here. Okay, so these two probabilities are same. Now this probability is what? It is basically that I have t0 here, then t1 here, and so on so forth. I have somewhere I have ti k, and then I have ti k plus 1. So it says that ti k plus 1 is finite. That clearly means that t naught I, t1 I, tki, all of them has to be finite. There is no question about that. This is finite means all of them has to be finite. Okay. So I can write this one as that this one is finite plus this interval, this time difference is finite, and this time difference is nothing but si k plus 1. Okay. So this one is finite, and then this time difference is also finite, which is nothing but ti k plus 1, sorry, si k plus 1. So I can write that probability given x naught equals to I, that ti k plus 1 is finite is same as probability conditional probability given that x naught equals to I, ti k is finite and si k plus 1 is also finite. And these two events are equivalent event in the sense that if this one is true, then this one is also true. On the other hand, when this one is true, then this one is also true, conditioning on x naught equals to I. Okay. So now we know that probability of A intersection B can be written as probability of A given B into probability of B. So, in this case take this one is B and this one as A, this is A intersection B, which can be written as probability of A given probability A given B multiplied by probability of B. Only thing is that here the condition that x naught equals to I is there, that I have to keep everywhere, okay, that I have to keep everywhere. And now we have this. Now the next second part, because of this assumption, the second part is basically equals to Fi k, because again the second part I can write as Pi Vi k is greater than Ti Vi not k, Vi is greater than k, okay. Pi Vi is greater than k because these two events are same, under the condition that x naught equals to I, okay. So, this part is basically same as Fi to the power k. So, I have written this one here, this probability is same as Fi to the power k. Now, I have to find out the first one. And to find out the first one, just recall the distribution of Sk, this Sik. We have pointed out that given that Tik is finite, the distribution of Sik plus 1 is same as the distribution of Ti starting from I, okay. So, we have proved this thing, earlier that, well, this lemma we have seen in the last lecture, that if the distribution starting from I, that Si k plus 1 is finite, this is equals to n, given that Tk I is finite, is same as distribution of starting from I have T1I, which is Ti also, T1I is equals to n, okay. This distribution of this one is actually given same as this one, it is basically using the previous lemma in the last lemma we have discussed in the last lecture. So, using that we can get this one, okay. Now, and it is true for all values of n, this is true for all values of n. So, if I take the sum over n on both the side, that basically mean that this side is nothing but, it is basically all possible values of n. So, it is nothing but Pi Si k plus 1 is less than infinity, given Ti k is less than infinity, okay. Because if I take all possible values of n here, so Si k plus 1 take all possible value, and so Ai k plus 1 takes value 1, 2, 3, 4, 5, 6, so on so forth. So, finally, that means that basically that Xi k plus 1 takes all finite values. So, Si k plus 1 is less than infinity. Similarly, if I take the sum in this side, that turns out to be Pi Ti1, which is same as Ti, is less than infinity, okay. This part is this one, and this probability we have taken to be Fi, here. So, that means the first part of the probability is Fi. So, finally, we get Fi to the power k plus 1, okay. So, we have shown that under the assumption that the statement is true for k, we have shown that the statement is true for k plus 1 also, and that completes the proof using the mathematical induction, okay. So, we have proved that starting from I, Vi greater than k, the probability of Vi greater than k is same as Fi to the power k, where Fi is nothing but Pi, Ti is less than infinity, and this is true for all values of k from 0, 1, 2, so on so forth, okay. So, this is the distribution of Vi. Now, let us again revisit the transient. Just recall that in case of the recurrent, we have shown this result. Recurrent, I is recurrent if and only if starting from I keep on visiting the chain, keep on visiting the state I throughout the excursion of the chain, throughout the process of the chain. Okay, throughout the, I mean, when chain goes to the future times, the ith state come back again and again, Okay, that statement we have seen earlier. So that basically mean that if a state I is recurrent, I will see the state again and again. If one state is seen again and again after some times, then that state is recurrent one. Okay, very layman word, or very loosely speaking, that is basically the recurrent state. Now, in case of the transient, the scenario is just opposite. The statement is exactly same here, probability statement, only difference is that here it is 0, here it is 1. Okay? So, it says that a state I is transient if and only if pi x n equals to I for infinitely many n is 0. Okay, and this is a necessary and sufficient condition. Both of them are necessary and sufficient conditions. That means if I can able to show that, then I is transient. If I is transient, then this is true. Similarly, in this case also, if I is recurrent, this is true. On the other hand, if this statement is true, then I has to be recurrent. Okay. So this actually shows that this actually give these two things actually give me the, I mean, intuitive idea behind transient and recurrent state. Recurrent state means it will keep on visiting, but for the transient state, it is sure, I mean, surely I will not visit the state I for infinite number of time. Okay, surely the state I will not be visited for infinite number of times. That is basically this statement mean. So that means that for transient state, after some finite value, the transient state will not be visited. Okay, will not be visited. So the proof is very simple. Notice that this statement is basically equivalent to write this statement, that number of visit to state I is infinity. Okay, that I is visited for infinitely many n, that basically mean that number of visit to state I is infinity. Okay, now this probability is same as this limit. The reason being that if you take k goes to infinity, that means this k, when this k goes to infinity, that vi is greater than any finite thing. So vi is infinity. Vi is greater than any finite thing, that means vi is infinity. That's why this probability is same as this limit of this probability. Probability pi vi is equals to infinity, same as limit k goes to infinity, pi vi is greater than k. Now, because we know that pi greater than k is same as fi to the power k, so this quantity is same as limit k goes to infinity fi to the power k. And in case of the transient state, we know that fi is less than 1, that is the definition, because fi is nothing but probability I t I less than infinity, and we know in case of the transient state, by definition this quantity is 1. So that means that this quantity is less than 1, that means this limit is 0. So that means that pi x n equals to I for infinitely many n is 0. Okay. So this actually, this corollary and remark, the main takeaway from this corollary and remark is that the intuitive idea behind the recurrent state and transient state. Recurrent state means these will keep on coming after some times, but transient state, after some finite time, that state will not be visited again. Okay. So with that, let us proceed and let us now see another set of necessary and sufficient condition for recurrent and transient. So this is one set of necessary and sufficient condition for transient, this corollary and this remark. Another set of necessary and sufficient condition for recurrence and transient are given here. So it says that a state I is recurrent if and only if summation n equals to 0 to infinity p(i)(i)n equals to infinity. Just recall that we defined Pijn to be probability that xn equals to j given x naught equals to I, and we defined Pij 0 is equals to 0 if I not equals to j and 1 if I equals to j. Okay? This way we have defined. So, it basically says that a state I is recurrent if and only if summation I equals to 0 to infinity Pijn is infinite, and I is transient if and only if the same sum is less than infinity. So, the sum, if this sum is finite, I is recurrent means that this sum has to be infinite. On the other hand, I is transient implies that the sum has to be finite. On the other hand, if the sum is finite, then I is transient. Okay? So, this is one way to show to check whether I is recurrent or I is transient or not, and the way basically we need to find out all the values of Pijn, and then I need to take the sum, and if the sum is finite we can directly tell that I is transient, and if the sum is infinite I can tell that I is recurrent. Okay? So, now let us go to the proof. So, proof is basically very not very difficult proof. Actually, what we are going to do is that we are going to prove the first one. Okay, we are going to prove the first one, and if I can prove the first one, the second one automatically follow from the first one. How? Suppose that we have already proved the first one. Okay, so now I have to prove two things, that if given condition is that I is transient, we have to show that this is finite, this sum is finite, to show that summation Pin is finite. Okay? And n runs from 0 to infinity, Now, so I can go in this way. So, I is transient given, I have to show this one. Suppose if possible, assume the sum n equals to 0 to infinity Pin is less than infinity. So, what I am doing is that if possible, suppose this is not true. So, that means this quantity, I am sorry, this will be finite. This quantity is not finite, that means this quantity is infinite. And if now I can prove the first one, this one is finite, implies that I is recurrent. Okay? And that is a contradiction, because I start with I is a transient, I get I is a recurrent. So, that is a contradiction. That means what I am assumed here is not true, and that means this one is true. Okay? So, I is transient implies that this one is finite. Similarly, if I assume this one is finite, then if possible I take I is recurrent, and if I is recurrent, then this one has to be infinite, and that is a contradiction. So, clearly if this one is finite, then I is transient. So, that means that if I can able to prove the first statement, I am done with both the statement, because the second statement automatically follows from the first statement using the contradiction. We can prove it by the contradiction. Okay? So, let us look into the proof of the first one. So, first part we have started with that, suppose it is given that I is recurrent, and I want to prove that the sum is infinite, and I want to prove the sum is, suppose that I is recurrent, we want to show that Pin is equals to infinite for I when I am taking the sum n equals to 0 to infinity. Okay? So, let us recall the definition of a recurrent state, which is nothing but Fi is 1. Okay? The definition of the recurrent state is Fi is 1. Now, you see that in this case Pi Vi equals to infinity, that means ion keep on coming to the state I again and again, that probability is 1. Okay? That probability is 1. Now, you see now that means Vi takes the infinite value with probability 1. So, if I now try to calculate what is the expectation of Vi under x naught equals to I, that is nothing but the value multiplied by the corresponding probability, which is basically infinity. Okay? So, expectation and the conditional expectation of Vi given x naught equals to I is infinity if I is recurrent. Okay? So, I write this one exactly here, that infinity is equals to Vi Ei Vi. Now I just plug in the definition of Vi here, and because expectation is a linear operator, I can take this expectation inside the summation side and I get this one. This is nothing but the generalization of this kind of thing, that if I have x1 x2 x1 plus x2, that I can write as expectation of x1 plus expectation of x2, and this is of course for finite one and this is for infinite one. So, you can take this particular thing is basically nothing but some kind of generalization of this particular kind of statement what we know. Okay. Now, if I take now the expectation here, recall what is Vi, what is delta I xn. Delta I xn is nothing but taking value 1 if xn equals to I, and it takes value 0 if xn equals to 0. Okay. So, now if I try to find out what is the expectation of delta I xn, that is nothing but 1 multiplied by the probability that xn equals to 1 multiplied by because the condition will be there I x naught equals to I, and then xn equals to I plus 0 times probability that xn equals to xn not equals to I. This is not equals to I, am sorry, this is not equals to I. Okay. This delta I xn is 1 if xn equals to I, and it is 0 if xn not equals to I. So, that means that if I try to find out the expectation of delta I xn, which is the value of delta I xn multiplied by the probability plus value of delta I xn multiplied by the probability of this event, okay, multiplied by the corresponding probability. So, that turns out to be this, and this term do not contribute anything, this one I can remove. So, finally, I get it, expectation the conditional expectation of delta I xn given x naught equals to I is same as Pi xn equals to I, which is written here. Okay? And this quantity is nothing but our PIIN. This quantity is nothing but our PIIN. So, this shows that if I is recurrent, we have shown that Pi summation PIIN sum is over n equals to 0 to infinity is same as infinity. Okay? So, one side is done, that if I is recurrent, we have shown that the sum is infinite. Now, I have to show the other side, that if this sum is infinite, I have to show that I is recurrent. Let us look into that. So, now suppose that summation is summation is infinite, we want to show that I is recurrent. Okay? I is recurrent. So, the way to prove this one is again by contradiction, that if possible let us take that I is transient. If possible, let us take that I is transient. So, if I is transient, then Fi is less than 1, this is by the definition of the transient state. So, what I have now is this one, that this quantity is same as this, that I have exactly shown here. We have exactly shown here, forget about this infinite, whether it is finite or infinite, forget about that. We have shown that this is same as this, it does not matter whether I is recurrent or I is transient, only thing is that if I is recurrent, then this expectation is infinite, and that shows that this expectation is infinite. So, this is the same process I can use, and I can claim that this equality hold true, this equality hold true. Now, we have used a fact which the proof I am not given here, but I use this one as a fact that tells that for a non-negative integer values random variable x, the expectation of x can be written in this way. Okay? The expectation of x can be written in this way. This is nothing but summation n equals to 0 to infinity, probability that x is strictly greater than n. Exactly, that is what we are going to use here, because Vi is the number of visit to state I, and that has to be a non-negative integer valued random variable. This Vi is a non-negative integer valued random variable. Okay. So, I can use this fact on Vi, only thing is that, well, I have this condition with respect to I here, I have to keep that one here also. So, now it can be written that Vi is strictly greater than R, and I have to take the sum over R. In this case I have written in terms of n, here I have written in terms of R. Okay. This probability I have already found out, this is nothing but equals to Fi to the power R, this is not in bracket, Fi to the power R. This probability is basically Fi to the power R, and when I do this sum, that is basically nothing but a geometric progression, and Fi is less than 1. So, it is an infinite geometric progression, and this sum we know it is nothing but 1 divided by 1 minus Fi, because Fi is strictly less than 1, and because Fi is strictly less than 1, this quantity is finite. Okay. So, this shows that if I is transient, then this summation has to be finite, and that is a contradiction, because we have started with that summation Pin is infinite. That is a contradiction, the fact that the summation Pin is now finite if I assume I is transient. So, I has to be recurrent. So, this assumption is wrong, and I has to be a recurrent state. Okay. So, that completes the proof, and as I mentioned that this example is these two condition is very helpful to prove different kind of result regarding Markov chain, to check whether whether for a given Markov chain a given state is transient or recurrent. These two results can be used. Okay. Now we are going to talk about a theorem which basically deals with finite state Markov chain. So, what this theorem says? The theorem says that suppose I have a Markov chain Xn which has finite states, the S which is the state space which is finite. Okay. So, that means that number of states in the state space S is finite, and I can write in this manner that there may be n number of states. Okay. If I assume that there is capital N number of states, then basically the state space can be written in this particular form. Now, in that case, when I have a Markov chain with finite state space S, then the theorem tells us that there has to be at least one recurrent state. Okay, there has to be at least one recurrent state. So, the theorem says that for a finite state space Markov chain, there has to be one recurrent state, at least one recurrent state, and there could be many, there could be more than one, but at least one state among the state space has to be recurrent. And the basic intuition behind this is very simple. The intuition is as follows. See, when I have finite number of states, suppose I have 5 states, for example, suppose I have 5 states. Now, when the Markov chain actually evolving with time, then as the time increases, Markov chain has to be in one of the state at least. It cannot be go out of this 5 state, because this is the whole state space. So, it has to take value from this 5 states. So, that means at least one state has to be visited infinite number of time. The reason is as follows, that if all the states are visited finite number of times, suppose the state 1 is visited n1 times, state 2 is visited n2 times, and so on so forth, state 5 is visited n5 times, then if you think this number that n1 plus n2 plus n3 plus n4 plus n5, then okay, I know where the state the Markov chain will be in the state space up to that time. Now, if I go add up one more time to that, that means n1 plus n2 plus n3 plus n4 plus n5 plus 1, where the Markov chain will be? Markov chain will have to be in some state inside the state space. So, that means it is not possible that all the states are visited only finite number of times. So, that is basically the intuition behind this particular theorem. Now, we will see that how we can write this one mathematically. So, the proof goes like that. Let us start with that the state space is given by this, where capital N is finite, capital N is integer and a finite positive integer. So, capital N is finite and positive integer. Okay. So, that is our state space. Now, look into this expression. Let us first decode this side, the right hand side. So, let us talk about the inside one. So, if I take I equals to 1, the inside summation is summation j equals to 1 to small n delta 1 xj. What is that? Recall that we define delta cx is equals to 1 if c is equal ex is equals to c and is the 0 otherwise. So that way the delta 1 xj is 1 if at the time step j I visit the state 1. If at the time state j I visit the state 1, then basically this quantity will take value 1, otherwise this quantity will take value 0. Now when I take the sum, that basically going to give me number of times the state 1 is visited after time 0 excluded, after time 0 till time n. Okay, between time 1 to n, how many times the state 1 is visited, that can be written in this particular form. Similarly, when I take I equals to 2, that is basically nothing but delta 2 xj, which is basically again nothing but number of times the state 2 is visited, between times 1 to n. Okay, and so on so forth. Finally I have summation delta capital N xj sum equal 1 to n, that is basically number of times the state n is visited between times 1 to small n. Okay, so these are the quantities inside for different values of I taking here. The first quantity is nothing but number of times state 1 is visited, second quantity is number of times state 2 is visited, and so on so forth. Finally the last quantity here, when I take I equals to capital N, this quantity is nothing but number of times state n is visited between the time 1 to small n. Okay, now if I add up this thing, that is nothing but total number of time the state 1 is visited, state 2 is visited, state 3 is visited, state 4 is visited, so on so forth. Finally the state n is visited between time 1 to time small n. Okay, and that is nothing but small n, because the state has to be any one of the state in the time 1 to n. So that means if I add up how many times the state 1 is visited, how many times the state 2 is visited, how many times the state capital N is visited, that will going to give me the number of step that I have taken. Okay, so that's why basically if I make this sum, that double summation in this side, that will going to give me small n, which is basically nothing but number of steps I have taken from time 1 up to the time n, which is basically nothing but small n. Okay, so we have this particular quantity. Now you see that if I take the limit on both sides of this particular expression, if I take the limit on the both side of this particular expression, I have limit n tends to infinity small n is equals to limit n tends to infinity double summation. The first summation is over I equals to 1 to capital N, the second summation is j equals to 1 to small n delta I xj. Okay, of course this side is infinity because I am taking the limit of n tends to infinity, so this side is infinity. Now look into this side. This side, you notice that capital N is finite. Capital N is finite here because the state space is a finite state space. So capital N is a finite number, finite integer. So easily I can interchange the limit and the first summation, and I can write this quantity is equals to limit n goes to infinity summation j equals to 1 to small n delta I xj. Okay, so that means that if you look into this part is nothing but I am taking the limit on each of these quantities as n goes to infinity, as small n goes to infinity. Okay, now this summation has to be infinite. Okay, this summation has to be infinite, and this is a finite summation, this is a finite sum, finite number of sum is here. So that means at least one of this quantity has to be infinite, at least one of this quantity has to be infinite. Okay,
at least one of this quantity has to be infinite. So this means that if I take the limit on both of them, all of them, then at least one of the limit has to be infinite, because this equality has to true, this equality has to true. So this whole summation need to be infinite, and because this n is finite, that says that at least one of the inside quantity has to be infinite. Now let us call the corresponding I for which this quantity is infinite to be I naught. Okay, I say that it is for at least one I is there for which this one is infinite, and call this I is I naught. Of course we can have multiple for multiple I this quantity is infinite, that can happen, but I can tell for sure that at least for one I this inside quantity has to be infinite, and call this I to be I naught. So it says that taking limit on both the side, we get there must exist an I naught such that this quantity is equals to infinity. The limit, I just replace this small n with infinity here by writing the limit there. So basically this quantity has to be infinite. Okay. Now what is this quantity? This quantity is nothing but number of visit to the state I naught starting from 1 up to infinity, up to the time infinity. Okay, so total number of visit to the state I naught, this is basically this, and that quantity is infinity with some positive probability. That means the state I naught will be visited again and again, and that says that the state I naught has to be a recurrent state. Okay, so this theorem give us a very nice thing, that if I have a finite state Markov chain, I can directly tell that, well, the Markov chain is there exists at least one one state in the Markov chain which is recurrent. With that I stop, and thank you for listening.